that. The California Association of African American Superintendents and Administrators, or CAAASA, and the University of California Los Angeles Center for the Transformation of Schools put this project together to support equity in virtual learning as we all shelter in place to prevent the spread of COVID-19. This work has been made possible by the generous support of the California Collaborative for Educational Excellence, or CCEE. We are grateful for their partnership on behalf of California's K-12 public school students. At the end of our live session today, I'm going to ask you to complete a survey to evaluate our time together, and it is our hope that you would really fill out the survey, because your feedback is essential to us making sure that the sessions continue to meet your needs. And if you're watching a recording of an earlier conversation, please do complete the survey as well. What I'll let you know too is I saw some questions already coming through in the chat, is that at the end of today's session, in addition to sharing the survey with you, I'm also going to share the link to the website, which will give you the opportunity to access the resources from today's session, which includes the recording, the slide presentation, and in addition to additional access to the same survey that I mentioned, you'll also have the opportunity to share follow-up questions that may not be answered during today's session. What will happen later on is that we will provide you with the opportunity to ask questions toward the end of the session. But as I mentioned, if you're not able to get them answered today, please don't worry, because you'll be able to click the link on the website that says follow-up questions, and you can enter your questions there. And so just really kind of thinking about today's session, I want to welcome you to this session with Ken Wesson. Today's session is called Homeschooling 101, what every parent and educator needs to know about how children learn, parents as teachers, study schedules, and setting expectations. So I'm going to go ahead and pass it on to you, Ken, and I'll be here monitoring the chat and providing support as needed.
Okay, thank you very much, Africa.
You're welcome.
And welcome, everyone. This afternoon, I'd like to share with you some of the research behind how children learn. And some of this, if you are educators, you may have seen an issue of the Educator for California, and I wrote an article for them on the science of learning. And so we will talk about the science of learning and the neurobiology behind how children learn and the kinds of things that we can do at home to enhance learning for all kids. Alvin Toffler, the futurist, said, "The illiterates of the future are not those who cannot read or write, but those who cannot learn, unlearn, and relearn." And we're in the process of unlearning much of what we learned about how children learn and where they learn. And instead of recognizing or basically identifying the learning space as a school, we have to recognize that learning takes place anywhere the brain happens to be. And right now, those brains are at home. And so we have to unlearn the old notions of classroom learning and make that shift and say, kids are going to learn everywhere we give them an opportunity and the kind of support necessary for learning to take place. So this afternoon, we'll talk about research from educational psychology, learning theory, and cognitive science, but we'll focus on how does the brain learn, and are there particular strategies and practical tips that can make learning easier at home. And we'll focus on math and ELA because those are the areas where many of our kids have some of the greatest difficulty. I used to work at on a math program up at Stanford, which at one time was the most widely used math program in the country. And so I'll share with you some of the tips that we learned in mathematics that will be very helpful for both parents and teachers to deploy with students at home. I'll also give you some strategies behind how we can enhance learning in ELA, as many of our kids are good learners, but they're not always good readers. But we can make those good learners good readers, and we can do so very easily. Second, which are the brain considered learning strategies and practices that are effective for all students everywhere? We say that anywhere the brain goes, it's going to learn. And sometimes it's learning things we don't want it to learn, but all brains are indeed learning. And it's our job to make sure they're learning the right things in the right places for the right reasons. And then last, how can parents reinforce the underlying thinking strategies behind math, ELA, and science at home so our students will excel or at least not fall behind as we shelter in place and they're away from their classrooms? What we find is that there's a tremendous gap between research and practices. We say that in the United States, we're research rich, but we're practice poor. And I'm on the advisory board for the Korean Institute of Brain Science in South Korea, where we produce some of the highest scores in the world for math and science. And it's because they've closed that gap between research and practice, and they use some of the best research and they apply to every classroom. The problem is most of the best research is actually taking place in the US. We're just not using it, and everyone else in the world is. So we're going to talk about brain basics and homeschooling basics, what we call 101, for both parents and teachers. And we say that parents are indeed their child's first teacher, and sometimes they're really the child's best teacher. And it's just up to every parent to understand, how is it that my child learns best, and then give them the opportunity to maximize his or her potential. But let me start with a very quick quiz. We ask, what percent of your brain do you use? Some people say 10%, some say 20, some say 50, some say 100%. So just take a moment and jot down, what is your answer, A, B, C, or D? Just take 10 seconds, think that through, and give us your answer. Now, while many of you probably said 10%, 10% is not the correct answer. We actually use 100% of the brain, and we can identify that through PET scans, where we can see the entire brain active in cortical processing when students are solving problems. The figure 10% actually came from early neuroanatomists who were able to identify only 10% of what the brain did. And a science researcher from the New York Times wrote an article saying that we used 10% of the brain only because that was all they could identify at that time. But we use 100% of the brain, and we have ample evidence with brain imaging technologies today. So we ask, exactly how does the human brain work? How does it learn? And how does it learn best? And over time, the brain has been likened to a radiator, a clock, a machine, and a computer. But the brain is actually a biological organ, and the brain is nothing at all like a computer. If we were to construct a computer that matched what the brain could do, that computer would be probably the size of North America. Most people learned that there's a process called stimulus and response by which we learn. Stimulus and response works very well with animal research, but not with human beings, and not with how the brain learns, and particularly how does the brain learn academic information. The universe that we reside in looks very much like this, but quite interestingly, the 3-pound universe inside each head, the brain, looks almost exactly like the universe in terms of how it's pictured. David Perkins at Harvard said, good thinking is a matter of making connections and knowing what kinds of connections to make. And that's the whole purpose of having a brain, is to make connections. And inside your brain, you have 100 billion neurons that are responsible for making all of those connections. Quite interestingly, infants will sometimes go as long as 63 days without growing a single millimeter, but overnight, they'll suddenly grow as much as 1 full inch. However, with the brain is making connections 24/7. Even when we're asleep, the brain is making connections. And oftentimes, the brain is making connections with information that we've encountered during the day, connecting it to what we already know. That's how we learn, and that's how we learn best. When the brain makes those connections, they're not metaphorical connections, but they're literal connections where the brain is physically connecting itself to other neurons. And it's those important circuits that get built that represent all of our knowledge. And we say that inside the brain, you have as many neurons as there are leaves or trees in the Amazon rainforest. However, the number of connections they make is comparable to all of the leaves on all of the trees in the Amazon rainforest. And that's how phenomenally powerful the human brain is. But the brain does something quite interesting. If I had a tennis ball and threw it to Africa, we use brain cells in a very interesting way. And the brain builds itself based on experiences. If I threw a ball to Africa, what happens is the color yellow goes to one part of the brain for processing. The round nature of the ball goes to another part of the brain for processing. The word tennis goes to a different part of the brain for processing. Africa's name becomes part of that network because it's part of that same episodic experience. But it all comes together to produce the image inside the mind's eye of yellow tennis ball. When a child is having difficulty understanding a new concept that's being introduced, one of the best things a parent can do is to say, this is like a yellow school bus. It's like a yellow taxi, connecting it with what a child has already been exposed to. We say it's like a yellow egg yolk, like a yellow banana. The whole purpose of having a brain, as we say, is to make connections. And as much as we talk about the acquisition of knowledge, knowledge is not really acquired. Knowledge is integrated with what we already know. And that's how we build the networks. That's how kids learn. That's how they remember. And that's how they learn and develop. And this is why we have something called the 10-80-10 rule. And that is that if we're introducing a new concept, what we want to do is build bridges from what a child already knows to the new content, help them make a connection, and then spend time on the new information, and then spend 5 to 10% of the time previewing the future connections that we're going to be making. And what the brain does is it begins to anticipate those connections, and once that new information is introduced, they make that connection quite readily. We were doing some work in McAllen, Texas, and one young boy kept insisting that bananas were brown, not yellow. And this is because he was a very poor boy and he had only seen brown bananas. We all make connections inside our brain based on our experiences. And sometimes the greatest amount of convincing is not going to change what's already existing in our brain in terms of circuitry. And what we say is that all brains are currently under construction, and particularly the brain of a child. And it's our job as educators and parents to recognize that kids are growing, making connections. And sometimes it takes a while to make those connections. The connections are not automatic, and they don't spring forth as a consequence of just exposure. They have to build those networks, they have to believe in those networks, use those networks, and then they become a real part of his or her experience and his memory. Even mistakes. We say that if you could go back and eliminate all the errors you ever made in school and life, you would erase yourself. And we say sometimes the best teacher is our last mistake. And it's by making mistakes and correcting them that we build new circuits that represent the knowledge that we've gained. So we ask, well, what do all brains need the most for proper functioning and for efficient learning? There are 6 things, and a lady from Australia put this together for me. I thought it was quite interesting. First, if you look at this, it's WESSON, but the brain requires water, exercise, movement, sleep, activities, and nutrition. And we can go 3 weeks without food or nutrition, 3 days without water, 3 days without sleep, and only 3 minutes without oxygen. And in all cases, if we exceed each of those figures, we begin to sustain irreparable brain damage. But all kids need exercise, they need movement, they need sleep. And today, with today's technology, we're finding that many kids are not getting the adequate amount of sleep, and consequently, they're having difficulty learning. Movement. By simply standing up, you add 5% more glucose to the brain, which actually fuels the brain. By moving, you get from 5 to 15% more glucose sent to the brain. By giving your kids a chance to move, you actually give them a 15% cognitive advantage to learning material. And this is why I mentioned the importance of letting kids walk while they're reading. And what you'll find is that many kids will actually learn more, recall more by walking while they read. Attention. Our brains can process about 4 billion bits of information every second, but we narrow that down to about 2,000 bits of information. That's what we call focus and concentration. And as we look at how each brain is different, because we've had different experiences, we find that many kids have slower processing brains. Instead of processing consonant sounds at 8/1000ths of a second, they take sometimes as much as 3/10 of a second per sound. And they'll ask things like, can you say that again? Although they've been nodding that they understood what you're saying. What happens with those kids is that when you finish the second sentence, they're in the process of still processing the first sentence. You've now given them the third sentence and they miss the second sentence completely. And this is why kids will ask a teacher to repeat the instructions several times, because they have what are called slower processing brains. With your kids at home, one of the things you can do is when you give them instructions, ask them to repeat the instructions in their own words. And what you'll find is they'll begin to, if they are slower processing brains, they'll begin to pick up and make those connections considerably faster. Equally important is attention span. And attention span is governed by age. And I've identified here approximately how much time we can actually teach a lesson to a child before we need to either give them an opportunity to talk about what they've learned, move on to a different lesson, or help them make connections and applications. Kids in first grade should have lessons no more than 5 to 8 minutes long. Kids from up to 4th to 6th grade, 9 to 12 minutes. Middle school students, 12 to 15 minutes. And high school students between 15 and 21 minutes. And what we say is that every 22 minutes, we should give students an opportunity to talk about, what have I learned so far? When they can summarize what they've learned so far, then they're ready to move on and make new connections. But the attention span of each child is governed by age more than any other single factor. Another factor with movement is many kids have trouble sitting still. And so we oftentimes associate that with attention span. It has less to do with attention span than it does with human biology. And that is, our bodies were designed to move. And in one school in Maine, what we have kids do is all kids have a ball that they sit on. And rather than trying to sit on a hard chair, what they do is they spend more time trying to balance themselves. And what they do is they begin to forget they're trying to balance themselves, and they begin focusing, concentrating far more on the work at hand, and they subconsciously are balancing themselves, which keeps them alert. If you have kids at home who are fidgety, try to get an exercise ball, and you'll find that those kids will concentrate far more and sit far more still by having the exercise ball. I say that if you want to maximize learning, use what I call perks. And perks simply says kids should be taught lessons where we first identify a pattern, where they can see connections, use emotions, because emotions are really the cement of all learning. If we're not emotionally engaged, we don't care, we're not going to learn or remember. Then R is for relevance. If information is relevant to a child, the child will find that information engaging, and he or she will remember it best. And then there are 3 C's, and that is, first, content always needs a context. And too often kids don't get content in a context that helps them remember, or a context that's important to them, or a context that's realistic. When the context is realistic, understanding the content becomes dramatically easier. The 3rd C, and that's the one that's most important, and we'll talk about this again later, and that it should be cognitively appropriate, and that's appropriate to the age and development of that child. And as the brain develops, the brain is able to process different types of information on a more sophisticated basis with age and experience. And sometimes we introduce concepts that are beyond the child's cognitive ability to process, and kids struggle, parents are frustrated, and teachers are frustrated. I was doing some work with the state of Tennessee, and they've moved some of the math concepts from 5th grade down to 3rd grade in the name of rigor. And the teachers, parents, and kids are struggling because it's not developmentally or cognitively appropriate. And the last is S, and S is for sense making. If students are able to make sense of content, it's easier for them to recall that content and apply the content in the future. And this is where we use models and stories that sometimes make the sense-making process much easier. The other is when students write about what they've learned, they make sense of that content themselves. And that's one of the best and easiest ways for students to remember. Patterns. If you look at the center of this page, most of you will see a white diamond. That white diamond doesn't exist, but inside your brain, because you look for patterns, you see a white diamond. Anyone who teaches geometry will tell you that if there are no connecting lines, there is no diamond, but still we see a diamond. Here we have clouds, and some of you have driven with your child, and your child will look up from the car window and say, "Mommy, that cloud looks like a man, that cloud looks like a star, that cloud looks like an elephant." Something as nebulous as clouds, they see formation, and it's because the brain looks for form. And what we want to do is take advantage of that natural inclination of the brain to look for patterns. When teaching mathematics, instead of teaching kids by giving them a worksheet of almost identical problems, one of the best things to do is to have them look at the patterns, like looking at how is it that you make 10, instead of giving them problems where they actually add and get 10, have them make up the problems themselves. How would you make 10? And let a child begin to construct the knowledge behind building the number 10. Now, what are some of the best practices that all of us should keep in mind if we're learning at home? And first, and another question. A male goat was placed into a pen with a female sheep, and the sheep nursed and reared the baby goat until he became an adult. But we asked the question, once he became an adult, was he now attracted to female sheep based on his experience? Was he attracted to female goats based on his genetic program, or was he attracted to both? 10 seconds to think about your answer. Most of you probably say it is driven by genetics, because most of us have read and taken biology courses, and we've learned that genetics drive our behavior. It turns out experience actually trumps genetics. And there's an emerging field now called epigenetics, and we'll talk about that next week. But what's most important is, no matter what your genetic program is, experience trumps genetics. And experience determines how the brain develops. Experience will cause epigenetic changes in the brain and our entire biology. Epigenetics will change how the brain develops, and consequently our behavior will be a result of how that brain has developed. But it all begins with experience, and it's that behavior that governs how the brain develops, and vice versa. And it continues in that entire cycle. We say that the mind is what the body-brain does, and the brain develops accordingly. We say that also that the human brain has evolved most efficiently by doing, whether it's at home or at school, and not so much by listening, by watching, or by keyboarding, but the brain learns best by doing. Edgar Dale developed something called the cone of learning, and he said that we remember 10% of what we read after 24 hours, 20% of what we hear, 30% of what we see, 50% of what we both hear and see, and 70% of what we see, hear, and say, but 90% of what we do and what we say. It's the doing and saying that become the most important catalyst for learning and memory. Giving kids opportunities not to listen, and sometimes educators will stay up at as long as 2 o'clock in the morning developing what we think are the most powerful lectures possible. Students don't remember our lectures, they remember what they did. And this is why at the University of Arizona, Chemistry 101 is now called chemical thinking. And the professor lectures between 12 to 15 minutes, and the balance of the classroom hour or hour and a half is devoted to learning by doing and lab. But it's not listening. We don't learn by listening, we learn and remember what we do. And if you think about something that you learned in middle school or high school, most of you will recall not a great lecture, you'll remember something that you did. That's what we remember best. And this is because there's a tremendous cognitive advantage when the brain processes one event in multiple areas, not just listening, not just reading, but by having a full brain or full body brain experience where multiple areas of the brain are responsible for processing aspects of that experience. Math at home. Math is everywhere, and there's nothing more important. That's one of the takeaways for today. Math is everywhere. Parents who say math is in a textbook, math is on a computer, everything you do and say is about math. If you look at a window, the shape of a window, it's a mathematical form, it's a rectangle. Having a child look at the window, identify shapes around the house, identify shapes when they go for a walk, teach them how to measure shapes and how to measure area. When kids begin to see that math is everything around them, they say, aha, I understand math. And no kid says, I'm not good at math, because they've experienced every aspect of math. Teaching them something like getting the toy register, the toy cash register, and letting them play with money, have them buy things, give change. They begin to learn addition, they learn subtraction, they learn how to count money, but most importantly, they learn base 10 math. And most of what they learn in base 10 math can be translated into the metric system. And in high school chemistry and mathematics, they'll find that chemistry and science, they'll find that that's extremely helpful. But you can do something as simple as just getting forks and spoons and divide them up and show a child how addition and subtraction work. And they can visibly see the different objects and how the math behind the objects is the math about patterns and relationships. Doing something as simple as cooking, kids learn fractions. And if you bring your child into the kitchen every time you cook, have them do the measuring, and they'll begin to understand fractions, fractional parts, whole parts, and how they come together to produce a delicious meal. I have something called a BrainSight box, and a BrainSight box is simply taking a box like this, and if you get a box from FedEx, just take your BrainSight box or take your box and convert it into a BrainSight box. On one side, I just make holes for a child to place his hands through those two holes. And when a child does, we can take concepts like 3 plus 2, and a child places his hand inside those holes, and on the other side, a child feels 3 objects plus 2 objects and begins to process them in the mind's eye based on touch. When kids see the symbols 3 plus 2, those symbols are meaningless. But when kids can actually touch the objects and actually reproduce those objects in the mind's eye, then they begin to understand mathematics, and they begin to understand how to process mathematics when they see the symbols. But many of our kids have difficulty with visual imagery, but we create the visual images based on what we've touched and how we've been able to see the objects and bring them into the mind's eye for processing. We can ask the child, can you show me 5 objects? Can you show me 2 less than 5? Show me 3 objects plus 2 objects. Show me a circle, a square, a triangle. And have them feel the objects and reproduce them in the mind's eye. And what you'll find is those kids will get much better at mathematics than ever before. And this is what kids look like based on what they feel. And they're feeling geometric objects and identifying which object is a square, which is an octagon. By getting something, these are called attribute sets, and you can see you can teach a child how to place the object into a screen that matches the shape itself. You can teach the names of the shapes, but more importantly, mathematicians will tell you that math is not about numbers. Math is really about patterns and relationships. And you ask a child, how are these objects alike? How are they different? Have students begin to describe what are the differences, but color, shape, size. You ask them, how would you organize these objects? And how many different ways could you do so? And they can organize them based on color, shape, size, thickness, identify which objects have 3 or more sides, 4 or more sides, which have right angles, which have no angles, which are triangles and hexagons. But you can teach all of the words, all of the geometric figures best by having a hands-on opportunity. We can ask them to identify objects based on 2 traits, their shape and their size, the shape and the color, the shape and thickness, and so forth. And they begin to understand that it's not single attributes, but many objects have multiple attributes. This not only helps them with mathematics, this is going to help them when they get into biology and classification of animals. We can ask which object has a triangular shape and have them with rings, or you can do this with rubber bands or string, have them identify all of the objects that are triangular and what other characteristics are shared based on color, shape, size, and how do you establish membership in one or more groups. When kids begin thinking in this way and they see and do, what they're beginning to understand is abstract thinking. And for many of our kids, they struggle with abstract thinking, particularly when it comes to reading. Equally important, having kids draw math problems is one of the best ways for kids to remember when they have a problem like 3 plus 5 If they draw 3 objects, draw 5 objects, and count them together, they know that it's going to always be 8. But equally important, they begin to see that when you have 8 objects in total, if you take away 5, you have 3 left. And kids begin to see those patterns and relationships, and they begin to understand the math much better. It's now visualizing. Even more importantly, understanding the language behind mathematics. And here's a problem. There are 21 hamsters, 32 kittens at a pet store. How many more kittens are at the pet store than hamsters? Many of our kids struggle with problems like this, not because they can't do the math. They have problems because they don't understand the language behind the math. With these types of comparing problems in math, they require visual imagery, imagination. And kids can't add or subtract the right amounts if they can't visualize the problem. For many of our kids, there are some visual cues that they can draw. And once you give them the visual cues, they can actually perform the math. But it's a visualization that becomes far more important than the math. And later the symbols are easy, but the visualization is one of the most important first aspects in mathematics. Next, if your kid is having trouble with math, and particularly word problems, this sheet I use is very helpful and simply says, when solving this kind of problem, first I do X because, next I would do because. I can check the reasonableness of my answer by, and I can check the accuracy by. When kids begin to, this is what we call thinking mathematically. When kids begin to think mathematically, they can solve any problem, no matter what the problem is, if they have a process. And many kids don't understand the thinking behind processing mathematical information. But processing it verbally is how they learn how to process it mathematically. And procedural math is how we typically teach math. And most of you have seen problems like this, 98 times 56. And our procedures say we multiply the 6 times 8, we get 48, we carry the 4, and we bring it down to 58. And then we multiply 5 times 8, and we get to 40, and we get 490, and then we add those two together, and we get 548. The problem is with procedural math, if you make a tiny mistake, you get the incorrect answer every single time. This is what's called procedural math, and I've identified procedural math problems for long division with as many as 52 steps. And 52 steps, you're probably going to make a mistake, particularly for your child. For a problem like 98 times 56, the best way to do it is what we call sense-making math. And that's where we say 6 times 8 is 48. 6 times 90, representing place value. And then 50, because it's 56, 50 times 8 is 400. And then 50 times 90 is 4,500. If you add those together, you get the same number. Most importantly, for young kids, when they can see how we arrive at this number, the number becomes more meaningful and the process for arriving at that number makes sense. And for too many of our kids, procedural math becomes problematic because it involves memorization rather than making sense of mathematics. Many of you probably remember the David Letterman show, where he would always have the top 10. And if we look at the top 10 human fears, dogs is number 1 or number 10. Loneliness is number 9. Flying is number 8. Death is number 7. Sickness, deep water and drink, financial problems, and bugs, and heights. And guess what number 1 is? Speaking in front of a group. But actually, what's more frightening to most adults and students is algebra. And for many of our kids, when they see algebra, this is the face we see. But algebra is actually quite easy because algebra is always representing relationships once again. And here are 2 umbrellas and 1 cap costs $80, and 1 umbrella and 2 caps costs $76. Most adults see problems like this and they shudder. But if we say caps are represented by X, umbrellas are represented by Y, we know that 1X, 1 cap, and 2Y, 2 umbrellas, costs $80, and 2x plus 1y costs $76. If we take that information and we simply double the second equation, instead of 1 umbrella and 2 caps, we now have 2 umbrellas and 4 caps. And instead of this costing $76, we double that and it costs $152. And what we can do is actually subtract the first equation, the first picture, from the second picture. And we can cross out 1 umbrella, cross out the second umbrella, cross out 1 cap, cross out 1 cap from the top and the bottom. And now we have 3 caps left worth 72, that costs $72. Divide that by 3, and you get $24 for 1 cap. And this is the logical way to process those kinds of problems. We can also put that same information on a grid. And here we have 2 caps and 1 umbrella costs $76, and 1 and 2 umbrellas and 1 cap costs $80. And you see that we're increasing diagonally by 4 from 76 to 82, which means here we should have 72. And now once again, we're increasing by 4 and we go from 80 to 84. And if 3 umbrellas and no caps cost $84, we can divide 84 by 3 and get 28. And we know 28 goes here. And that's the cost of 1 umbrella with no caps. And 2 umbrellas and no caps costs $56. We can take 72, and that's the number of caps with no umbrellas, and divide that again by 3, and we get 24. We put 24 here, and this is the cost of 1 cap with no umbrellas. And 2 caps with no umbrellas is $48. And we see we're increasing by 24 here, we're increasing by 24 here, and diagonally, we're increasing by 4 each time. So we know what goes here, and here's our grid. And we begin to see how you fill out the entire grid based on those patterns and relationships. And suddenly, the equations you saw at first are simply representations of different points on the grid. And this is all algebra is really about. It's not about the caps and umbrellas, it's about the relationships. Teaching kids fractions. And each time you teach kids fractions at home, one of the best things you can do for them is share with them what those fractions look like in pictures, in fractions, percents, or decimals. Help students make those connections. Too often we teach these fractional parts not only in different chapters, we teach them in different years, and our kids struggle with them when they encounter them in another year, but it's the exact same relationship in terms of the whole to part relations. Science at home. I was going to talk about science at home today, but I recall that next week, May 13th, we will talk about science at home, and I'll share with you some great ideas that can be incorporated into the kinds of things that you can do at home with your child during the summer. But literacy at home. You can get all kinds of books available. There are books galore available to help your kids with literacy at home. But even more important, think about what we call active literacy, and that is ways in which kids take what they've read and actually can learn by doing, manipulating some of the concepts, manipulating the words, the vocabulary, based on what they've learned. When kids can make these kinds of translations, suddenly this is information that students are actually going to remember. But what we find is that many of the kids who perform poorly in school, and sometimes it's our kids, they're raised speaking non-standard English or some variation of English at home. And African Americans, they have something called African American, it's AVE, it's African American variation of English. But what we find is that when kids have a great overlap between how they use language at home the kind of language that's used in school and the kind of language that they use even outside of school at play. When there is a wide range of language that's reinforced, these kids do not struggle academically. But kids whose at-home language has very little correlation with the language used at school and the language that they use in school, these are the kids who are going to struggle academically, because basically English is a foreign language to them in many ways. And so we need to have linguistically responsive instruction that capitalizes on ways in which those kids can learn by giving them more language experiences through which they will learn. For many of our kids, what we find is that struggling readers oftentimes spend too much time on decoding, and 81% of our struggling readers actually have problems with vocabulary. But 100% of those struggling readers have problems with comprehension. And that problem with comprehension oftentimes is based on vocabulary, which means most of our kids need more practice in developing their listening vocabulary. That's the largest vocabulary that we have. And this is based on all the words that they hear and understand. The speaking vocabulary, giving them lots of opportunities to engage in discourse and dialogue, is how they develop that speaking vocabulary. Our reading vocabulary is actually the third largest, but that reading vocabulary increases by having lots of opportunities to write. And what we find is that kids who are good writers, they become good writers because they have lots of opportunities to read. And they apply the same style of writing based on the information that they've read. And one of the best things that we can do for our kids, and many of you know that buying books at Barnes & Noble and Amazon is very expensive. A couple of years ago, I worked with Aiken, South Carolina, where they have the University of Aiken. And so I spent some time down there at the university, but also spent some time with members of the Black community. And we developed what we call a community book exchange. And what we found is that as a consequence, they had a nice increase in student achievement and also adult literacy. What people did was they went to garage sales, thrift stores, their own libraries at home. They go to the local libraries. Sometimes libraries will discard books based on copyright date. They would get those books and they would bring them to one location, and that was the church basement. And they had a huge selection of books, and there are volunteers who would identify the appropriate age or grade level for the books. And people were invited to come in anytime to bring a book and take a book. And if you didn't have a book, just take one and bring it back. But what they found was that the pass around rate of the books was extremely high. Kids would actually go through books much faster than if they owned the books themselves. They would take a book, race home and read it, and bring it back and get another book. And what they found was that the student achievement rate for reading increased dramatically by simply having the community book exchange. And we can do this in every community in California, whether it's your community center, a local church, a school. Just give kids opportunities to have books at home. And what we find is that many kids who are poor readers don't have very many books at home. And in LA, they found that that wealthy kids had 16 times more books at home than poor kids. And that makes a big difference in terms of achievement. And by having the books, we find that the books that kids oftentimes read in school, the tier 3 words are the words that are typically discipline specific, but the tier 2 words are the words that they'll encounter with books. Tier 1 words are the words that kids already know, and they use words like book, run, see, tree. They hear and see these words all the time. The biggest challenge for kids is the academic language words that they'll learn by reading. And they oftentimes will not learn these words without opportunities to read more. And spending time on what we call morphology, and that's looking at all the ways in which the parts of the word bring meaning to the word itself. Full always means full of. Un means not. Pre means before. Therm always is associated with heat. By giving kids opportunities to look at the morphology of words, looking at the Greek and Latin bases of those words, and developing an understanding of the antonyms, how to associate those words with other words. The root word aqua always means definition, as in aquatic. When kids learn the root words, these are not the exclusive property of science, although these words are used in science. These words are used everywhere in literature. And when kids begin to understand how those words develop into the larger words, these roots help students understand reading content when they encounter new words. We look at prefixes, like hemi always means have. Hypo always means under, as in hypodermic, you put the needle under the skin. Meta always means change, as in metamorphosis. When kids begin to understand the prefixes, what they mean, and the words in which you'll find those prefixes, they begin to understand our language much better. The same with the suffixes. Ology always means the study of, as in neurology. Graph always means a written or drawn, as in electroencephalograph. These definitions connected to these suffixes is how students become better readers. The National Assessment of Educational Progress had one word, arthropod. Most of our kids struggle with this word, but arthropod is an invertebrate animal with an exoskeleton. And kids ask, well, what's an exo? An exo means external. And you say, well, name some. And here are some animals with the exoskeleton. And again, this is something you can find very easily from Google. And you say, well, what animals are those? With insects, crustaceans, and arachnids, they all have exoskeletons. They also have segmented body parts and jointed limbs. And if you've seen a lobster, you've seen an arthropod. If you've seen a crab, you've seen an arthropod. And you say, well, where have you heard the word arthro before? It means something related to joints. Well, how about arthritis? When kids can make these kinds of connections, this is how they begin to understand language and the words that they're going to encounter in reading in every discipline. I usually take those words and say, those are the growth words for kids, and we put those in green. An arthropod is a growth word. Invertebrate may be a growth word. Exoskeleton, all of the words that are new words for kids, these are the new words that become part of their personal vocabulary, and those are the vocabulary words that are going to help them in school, no matter what discipline they've encountered. Also are what we call the polysemous words. These are words with multiple meanings, and the multiple meaning words are the words that many of our kids struggle with the very most. And that's because they see words in only one context, but the words have multiple meanings. Think about the word scale, and I'll let each of you take 10 seconds to write down as many words, as many definitions for the word scale as you can, like musical scale, scale to weight. Write down as many quick definitions as you can for the word scale. Scale can be a verb, a noun, an adjective. It can even be a metaphor. And here are some definitions for the word scale. And you see there are 20 definitions. The machine, the noun for weighing, musical scale, skin, a leaf, the oxide formation on a metal. Okay. How about more definitions for the word scale? Okay. The Likert scale, you've all seen this from best to worst. Okay. There's a jazz scale, there's a wage scale, a scale model, geological time scale. Okay. Scale means as a verb to chip, to arrange in a graduated form. I've identified 78 different definitions of the word scale. And the more of these definitions that a kid has connected the word to, the easier it is for him to read and the greater his word comprehension is going to be as he navigates the school day. Now here's our reading list for the day. And so take a look at this reading list, please. And most of you will find this reading list somewhat intimidating. But I gave a presentation for the International Reading Association on how the brain actually processes multisyllabic words. if I ask you what is dactyloscopy, most of you would struggle if you just read the word and didn't hear me pronounce it. In school, we typically say, well, just break that up in its constituent syllables, dactyloscopy, and every time a child sees that, he goes through that decoding process and struggles. However, I developed what I call reverse direction decoding. And instead of saying dactyloscopy, just say this silently with me. Say P, and then say coupy, then loscopy, then tuloscopy, then dactyloscopy. And what you'll find is that you'll say the new word correctly every single time you encounter a new word by using this process. I use this with my students at the medical center, and these are medical terms that once broken into their constituent syllables, and say this with me, please. Say tis, litis, ulitis, ticulitis, verticulitis, diverticulitis. And once again, you'll say every medical term, every scientific term correctly the very first time you pronounce it. For a young child, all he or she needs to do is to go through a text and look at the words on the page that he or she is not familiar with. Use this process so they can pronounce the words, and then they read the entire text without ever stopping, because each time you stop, you begin to decrease reading comprehension. By using the strategy, you can read for fluency, and that's what increases reading comprehension. And this is how reverse direction decoding works. This is the biology behind how this process works and why it works so effectively. Marilyn Adams said, in fact, the automaticity with which the skillful reader recognizes words is the key to the whole system. The reader's attention can be focused on the meaning and the message of the text only to the extent that it's free from fussing with the words and the letters. And this is what decoding is all about, the words and the letters. And many of our kids who are in Title I, they spend more time in reading intervention, focusing on phonics, the words and the letters, rather than focusing on reading fluency and comprehension. And this information can be found online. If you Google reverse direction decoding, you'll see the article I wrote in Brain World on how that process works and why it's a biologically sound approach to teaching reading. A couple of other issues that should be important to both educators and parents. One is rigor, and the other is developmentally appropriate learning. And developmentally appropriate simply means having learning expectations that are aligned with the child's cognitive development. Okay. This is what rigor looks like for most kids, where the load is beyond the child's ability to perform. Okay. But as a child ages, certain skills develop, which means our expectations should be governed by age and brain maturation, because there are regions of the brain that actually mature on a different time scale. The brain doesn't grow like the body, where it's all proportional. Instead, different parts of the brain grow and mature on a different time scale. We have two hemispheres in the brain, and most of you have heard about left brain, right brain thinking. And anything you've learned about left brain, right brain thinking, please forget it, because to anyone in neuroscience, the notion is rather silly. All information is processed by the two hemispheres of the brain via a structure called the corpus callosum. And the corpus callosum is composed of about 300 to 800 million nerve fibers that connect the two hemispheres. And this is how we process 4 billion bits of information every single second. And it's the two hemispheres working in tandem. Neither hemisphere is ever processing information while the other is quiescent. The two always work in tandem. Now, if you look at this picture, I ask you, which does not belong? Which does not belong in this picture? Okay? And most of you shouldn't have any problem identifying what does not belong. However, if I ask you this question, which does not belong? Sun shines, moon glows, stars twinkle. Which does not belong? Each of you probably has an answer, and the answer can be justified, and for many children, it's justified based on age and maturation. Children between ages 3 and 5, they focus on the attribute of size, And they say the moon and sun are big, so we eliminate the stars. The stars do not belong. Kids between 4 and 6, they're now learning about the concept of number. And they say there's one moon, there's one sun, so there are countless number of stars, so the stars do not belong. In upper elementary, kids are learning that the moon actually reflects light. And because the sun produces light, the moon is reflecting light, and stars produce their own light, we say the moon does not belong. And high school and university level will tell you that the sun is actually a star, at which point we say the moon is not a star, the sun is a star, and stars by definition are stars. But as you see, with every age, we get different answers, and each answer is developmentally appropriate based on the child's age. However, the proper answer from the test makers was that the sun did not belong because it occurs during the day. The others are nocturnal events. However, based on reasoning, you can answer the question any of the other ways, and we see dominant answers based on age from our children.
Ken, I just wanted to hop in and say we have 3 minutes left.
Yes.
Question? All right.
Yes. Scheduling at home. A few things very important for those of you who are scheduling learning at home. First, there's nothing more important than being consistent, and that is having a designated time, a designated place in the home for studying. And if you have multiple children and only one device, the time and place becomes far more important. Okay? Make sure every child has an opportunity to learn, pardon me, with his or her time, but also a designated place in the home. And that means with that designated place, you also have an environment conducive for them to learn. And that is that we have a place for them to learn quietly. And for all initial learning, in order for kids to concentrate and build the brain circuits, it must be a quiet place for them to do so. When they're reinforcing and applying information, that kind of elaboration doesn't require as much quiet, but it does require a place for them to learn and a time for this to take place. In that environment, one of the most important things that we can do is to minimize distractions. And most of us have cable TV, and some homes have cable TV on 24/7 because it's available 24/7. Turn off the TV. And kids have the iPods, the iPhones, and the every other device possible. And they say, oh, I can listen to my phone, I can listen to my iPod while I'm working. And they call that multitasking. What we find from brain research is that kids really don't multitask. It's what we call continuous partial attention, CPA. And they simply shift. They're constantly shifting from one to the other, but they don't concentrate, which is why they don't learn. The last is always have an end of the day ritual with your kids if at all possible. And that might be something like a 2-minute paper where they simply identify what have I learned? Were any of my misconceptions or preconceptions overturned? What do I still need to know in order to understand this concept? What is it connected to, and what do I think will come next? By just giving a kid an opportunity to write about his thinking, you'll find that kids will actually become better thinkers. You can also tell them that tomorrow I'll be interested in hearing about what you have learned or thought about, and have them in the next morning do what I call FedEx thinking. The next morning deliver. What is it that they've learned, and how have they processed the information they've learned today? This is what we call a depth of knowledge, and that's what prompts long-term learning for all kids. Okay? And this requires that they have downtime, and that's some time for them to think about what they've learned. And when they have downtime, this is some of the most important time, because the word school comes from the Greek word skelion, or the Latin word skole, and that means leisurely time to think, leisurely time to solve problems. All of our kids need time to think. That's what fosters brain development, and that's how our kids will get better, and they'll be better prepared when school resumes. Okay? Once again, I'll ask you to just take a couple of minutes. I know we're at 2 o'clock, but if you just take 2 more minutes, and please write down what was the most valuable idea that you learned this afternoon, and what are 2 things that you'll do differently having had this conversation this afternoon, and how will this help your students at home or your students at school? And please jot down your answers.
I'll also ask that when you're putting in the chat, make sure that you're responding to all panelists and attendees so that everyone can see your answers.
And Africa, if you can share a couple of those with us, that'd be extremely helpful.
Sounds good. Teaching vocabulary differently, that we use 100% of our brain. Some folks about the math work that we're navigating through today. Continuous partial attention, or CPA. The learning environment and the box site learning activity was really cool. What we talked about with regard to decoding. Let's scroll and talk. There's like so many really cool things being added. Bridge, build, and extend.
Yes.
The different reverse decoding, reverse process coding. That there's no such thing as left brain, right brain. Yep, so some of these are repeats of some of the things that other people have said.
Excellent, excellent.
Yeah.
Well, we are going to develop a portal to ask questions.
Yes.
And those of you who have additional questions, please don't be shy about sharing those with us. And let me end with this slide. And you see inside this fish is a little tiny fish being protected by the mother fish. And what I say is that even on your very worst day, you're still your child's very best hope. Okay? Do what you can to both protect them, but also teach them to learn. The most important thing for them is preparing them for the future. Okay? And with that, if you do have questions, here's my contact information. And if I can help you, please don't be shy about contacting me.
Well, thank you so much, Ken, and thank you so much for everyone who was part of this session and with your engagement and your encouragement and your insights and your questions. I'm going to drop in the chat right now the link to the survey. And for those of you who are asking where you're going to get the resources from today, I was not ignoring you. At the beginning, I shared that. I'll drop in the chat right now the link to the website that I mentioned. And on the website, you'll be able to access the portal that Ken just talked about, where we'll have the recording of today's session, the slide presentation, and the opportunity to ask follow-up questions. And so it's a really great resource. If you don't grab the link right now, all of you who registered for today's session, which is how you got here, go back to that email and the link should be in the email that will take you to this website as well, and all the resources are there. All you have to do is scroll to look at the icon and the description for today's session, and you'll be able to access it. So thank you so much. I'm so glad you all enjoyed it. It was really very, very informative for me too. And hopefully I'll be hosting some more of these sessions. So hopefully I'll see you, Ken, and also participants in the future. Have a great rest of the day.
Good, and we'll see you next week when we talk about science.
Yes. All right. Bye-bye.
So long now.
Bye.